I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Irrational. We'll look at an irrational number that has charmed mathematicians for thousands of years and has been called the secret to beauty and harmony. Named the golden ratio, it equals 1 plus the square root of 5 over 2, about 1.618. Two side notes, one about pronunciation. As a student, I always heard professors pronounce this as phi, but fraternities and sororities go with phi. I'm not sure how to fit in faux or fum, so I'll use phi here. Also, phi has been given many names: golden ratio, golden mean, golden proportion, divine proportion, golden section. In German, this is golden Schnitt, which is hard to pass up, but I'll again go with phi. In telling a story, you usually want to start at the beginning, but it is very unclear where the beginning is with phi. There's a thought that the Pythagoreans revered it, but they left no writings, so that's just speculation. Euclid defined it in 300 BC and used it to construct pentagons and other geometrical figures. Some have claimed that such structures as the Parthenon, compute width divided by height, and the Great Pyramid were designed incorporating phi into their dimensions. Skepticism is warranted here. Notice that the bottom of the Parthenon rectangle is pretty arbitrary. In 1509, Luca Pacioli wrote a book about it, naming it the divine proportion, and trying to convince artists that this mathematical curiosity had amazing, even divine properties. The book was beautifully illustrated by Pacioli's friend, Leonardo da Vinci. This fuels rumors that Leonardo embedded phi in the Mona Lisa, The Last Supper, and other works. See the episode 2 Leonardos for more on this. In checking claims about the use of phi, you look for rectangles for which the ratio of the sides equals phi. Here are some difficulties with this. If you get a ratio of 1.59, for example, is that close enough? It's actually closer to 1.6, which is 8 over 5, a nice simple ratio of Fibonacci numbers that appealed to, among others, Leonardo. If you take any object and make enough measurements, you're likely to accidentally find a ratio close to phi. Is that numerology or a real discovery? In the absence of hard evidence, rectangular guidelines drawn in would help, especially if it showed specific properties of phi like we'll see later. Most experts are skeptical of claims about phi, and there is no evidence for the use of phi, for example, by Leonardo, Michelangelo, Raphael, or any other turtles. Sorry. At the very least, phi is extremely interesting mathematically. Let's see why. Here's Euclid's definition. Divide a segment of length A into parts of length B and C, such that A over B equals B over C. The common ratio, A over B or B over C, equals phi. You can get the precise value of phi from this definition. Choose A equal to phi and B equals 1, so A over B equals phi. By the construction, C equals A minus B, so B over C is B over A minus B equals 1 over phi minus 1. Then the equation A over B equals B over C becomes phi equals 1 over phi minus 1. Multiplying by phi minus 1, we get phi squared minus phi equals 1, or phi squared minus phi minus 1 equals 0. Any of these equations defines phi. We can use the quadratic formula on the last one to get phi equals minus minus 1 plus or minus the square root of 1 plus 4 over 2. And since we define phi greater than 1, we'll take the plus and get phi equals 1 plus the square root of 5 over 2. So phi equals 1.618033 and so on. What is phi squared? Well, first compute phi on a calculator from 1 plus square root of 5 over 2, and then square it. 2.618033, those decimal digits are the same. And that means phi squared seems to be phi plus 1, but wait, that's the same equation as phi squared minus phi equals 1 that defined phi earlier. What about 1 over phi? Try it on your calculator. 0.618033, we still have that same decimal part. Well, 1 over phi equals phi minus 1 is the same, multiplied by phi, as 1 equals phi squared minus phi, which is a definition of phi. Properties such as these prompted the astronomer Johann Kepler to call phi a precious jewel. Kepler used phi to construct some wacky and wildly inaccurate models of the solar system, illustrating the music of the spheres. Well, here's a geometric property of phi. Suppose you have a golden rectangle with dimensions 1 by phi. Cut a 1 by 1 square off an end. you're left with a 1 by phi minus 1 rectangle, which has ratio 1 over phi minus 1 equals phi, another golden rectangle. You can continue this forever, golden rectangle, and so on. There are many other fantastic properties of phi. One involves the Fibonacci numbers 1, 2, 3, 5, 8, and so on. Naming psi for the other solution of the equation for phi, psi equals 1 minus the square root of 5 over 2, and the nth Fibonacci number equals phi to the n minus psi to the n divided by the square root of 5. So phi to the 8th minus psi to the 8th divided by the square root of 5 is 21, the 8th Fibonacci number. Isn't that wild that raising those irrational numbers to powers and dividing by the square root of 5 gives a nice simple integer? Speaking of Fibonacci, there is a real usage of phi by nature that explains why the number of petals on a flower is likely to be a Fibonacci number. Think of placing petals in a spiral moving up a flower stem. If you placed them 90 degrees apart, after 4 petals went on, the next set of 4 would line up exactly with the first 4 and block out all the light. To get the best overall coverage of light, it's been shown that an angle of 222.5 degrees is best. Well, its complement is 137.5 degrees, those add up to 360, and 222.5 divided by 137.5 equals, you guessed it, phi. Infinite constructions have played a role in mathematics for many years. Continued fractions were commonly used in the 1600s through the 1800s. A simple example is 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 and so on. We can figure out what this equals. Start by naming it x, 1 plus 1 over 1 plus 1 over 1 and so on. Now notice that the first denominator is 1 plus 1 over 1 plus 1 over 1, which is x. So x equals 1 plus 1 over x, multiply by x to get x squared equals x plus 1, or x squared minus x minus 1 equals 0, and we have x equals phi. How about an infinite square root? Square root of 1 plus square root of 1 plus square root of 1 and so on. Again, name it x, and notice that x equals the square root of 1 plus, and all of that's the same as x. Square both sides to get x squared equals 1 plus x, and once again we have the divine proportion phi. Well, phi may or may not be divine, but it does show up in many places. There's a wealth of information in books and online about phi, but be aware that it's a popular topic for mystics, and many claims made have little or no basis in fact. But recently, say the last 200 years, much music and art has been made intentionally using phi to proportion sections. Bartok in music is an example. Have fun exploring the golden ratio.